Welcome to the 8th lecture of I to the L. Let's start with a lecture 7 recap. So in the last lecture, we discussed loss functions. We started with naive losses like the L2 versus the L1 loss. And we saw how each of these losses has its own characteristics and therefore optimizes for a different thing. Now, we then discussed how to go from the binary classification problem that we saw early in the lectures towards the multi-class classification problem and what kind of loss arises from that. So in the case of binary classification, we use our sigmoid to convert a score that we get here from our neural network to a value that can be interpreted as a probability, therefore a value between 0 and 1. In the case of the Softmax formulation, this is a multi-class classification problem, and we use exactly the same trick to go from the scores. In this case, we no longer have one score for 0 or 1 classification, but we have a score for each class. And the score for each class is converted using the Softmax to probabilities for each of the classes. So we have, for example, here this case where we have the probability that indeed the input is labeled as class 1, and this would be essentially the formulation, which takes into account the score of class 1 and then normalizes by the 3 scores of class 1, 2, and 3. We then move to the definition of a Hinge loss, which is derived from a multi-class SVM formulation, and we saw the differences between the Hinge loss and the Cross-Entropy loss. So essentially, the Cross-Entropy loss always wants to improve, so the loss never gets to 0, while the Hinge loss actually saturates. And this essentially means that at some point, once our score, the correct score, is high enough, therefore the network is really sure about the correct classification, the Hinge loss will give a loss of 0, which actually means do not optimize further for that particular input. In the last lecture, we also discussed in depth nonlinear activations. So these have really an effect in neural networks, otherwise we would just have a bunch of linear computations. So these really bring the power in towards creating this division in the energy landscape that can actually allow us to perform classification with a high accuracy. So we started with the Sigmoid activation, which is kind of an obvious choice coming from the binary classification problem that we saw earlier in the lecture. And we saw essentially how this causes a problem during the backward pass because the saturated neurons actually kill the gradient flow. And these are the neurons that are acting in this regime here at the extremes where, as you can see, the gradient tends to go to 0. And as soon as the gradient in this nonlinear activation turns to 0, this kills all the flow, all the gradient flow as we backpropagate through the network, which essentially means that we cannot train our neural network. So we then move to TanH activations. These still have the problem of the saturation, but they are zero-centered, and we discussed in the last lecture why not having zero-centered outputs is a bad idea. But we then move to the ReLU units, the rectified linear units, which are actually the units that we mostly use, especially with convolutional neural networks. And these actually give large and consistent gradients during backpropagation. So you can see here a consistent slope in the ReLU function. They do not saturate, and they actually provide a fast conversion of convolutional neural networks. The only drawback they have is that if ReLU is outputting 0 or is outputting or is receiving essentially a negative input, then we have what is called a dead ReLU. So this dead ReLU means that actually when we backpropagate, we also have gradient of 0 because we are basically working on this left side, which is not the active region of the ReLU, and this essentially means that we can again not train our neural network because this ReLU is essentially not doing anything for us. So as a quick guide, Sigmoid is not really used anymore in modern architectures, and ReLU is actually the standard choice, especially in convolutional neural networks. A second choice would be variants of ReLU like leaky ReLU or parametric ReLU or max out. And as we will see towards the end of I2DL, we will see that recurrent nets will require a TanH or similar function. We then moved towards initialization of neural networks, and we saw how initialization was extremely important in order for your neural network to train. And this comes partially from the optimization. So the optimization is a local optimization, which means that we're not guaranteed to reach the global optimum of the function. So the point where the algorithm actually tells us that there is the optimum depends highly on the initialization, which means that if I initialize my solver here, then it is very likely that I'm going to reach this point and the solver is going to say this is the optimum of the function, while if I would have initialized my solver here, then I would have reached actually the global optimum of the function. So initialization is extremely important to train neural networks. And we saw actually how the Xavier initialization really made things robust. So actually allow us to have large consistent outputs, large consistent gradients during backpropagation, and therefore our neural networks could train properly. And this was essentially just by ensuring that the variance of the output is the same as the variance of the input. Now, a small variation is required when we're actually using ReLUs, and this is because the ReLU kills half of the data. And you can see how this tiny difference in how we actually set the standard deviation for our distribution, where we actually take the weights with which we will initialize our neural network, how this tiny change from having 1 over n to having 2 over m actually leads to absolutely no training of the network. You see here that the error is not improving at all. But when we change it with this 2 over n value, then the network suddenly starts to train and the error starts going down. So this tiny change actually makes a huge difference, which actually speaks towards the importance of the initialization. Okay, so we'll start today with Lecture 8. Lecture 8 continues the trend of things that we actually need to properly train our neural network. And we will start with a very common technique that actually helps boost results, which is data augmentation. So we know that our classifier, let's say we're building a classifier for cats, and we know that cats can be found in a variety of poses. So our classifier has to be actually invariant to this wide variety of transformations. Now, transformations can appear in many ways. There can be pose transformations, the cat can be in different poses. There can be appearance transformations, so we have white cat, gray cat, brown cat with a lot of texture, let's say, on the fur. There can be illumination changes. The cat can be outdoors and it can be extremely light, or the cat can be indoors and it's extremely dark. So essentially, even if we just Google the word cat, we'll see all these different cats appearing with all these different poses, appearances, and illuminations. And our classifier actually has to be robust to all these transformations. So it needs to be able to parse all these images and say that all these images actually are showing the image of a cat. So in data augmentation, essentially what we're doing is we're helping the classifier. So we're synthesizing data by simulating plausible transformations. The most common types of data augmentation are very simply flipping and cropping. So we can see here one way of training a neural network. The first way is by using no data augmentation, in which you take your image, you crop it based on the input size that you actually need, that your neural network actually needs. In this case of AlexNet was 224 by 224. And you actually use this image for training. So in this case, you have one image to train your neural network. But what you can then do is you can then flip your image, right? So you have here the image of your cat, and you can simply flip it. So with this simple trick, what has happened now is that we are showing the network the cat as if I was looking, let's say, on the right side of the cat, and as if I was looking on the left side of the cat. So it is as if I took two images of that cat, and I show these two images on a neural network, and I'm telling my neural network that both of these images are actually showing the cat. So I'm making my classifier more robust by showing different views of the cat. Now another trick is to do cropping. And cropping actually means taking my 224 image and cropping different parts of the image. So in this case, you can see here just the face of the cat, here mainly the eyes, here mainly the nose. And all of these parts of the cat can be used to train my neural network. So essentially what I will do is I will take these 5 crops of my image. I will perform flips on all of these images, on all of these patches, all of these cropped images, and suddenly I have 10 images that I can use to train my neural network. And you might ask, well, why is this cropping actually effective, right? So sometimes the cat is half-occluded. So in this case, even the ears of the cat cannot be seen because it's wearing this, I think it's kind of a hat. And so generating artificially this kind of occlusion, so not really showing the full object to my neural network, actually helps my neural network become more robust to occlusions, partial occlusions, or objects that are just placed on top of my object of interest, or on top of my cat in this case. So essentially with data augmentation, what I have done is I have converted one image to now 10 images that I can use for training. So I've basically augmented my data set to train my neural network. Now we can also simulate other types of image changes. For example, we can apply random brightness and contrast changes to the image. So in this case, I've simulated as if my cat was, for example, indoors where the environment is darker, and then moved outdoors where the environment is slightly brighter. So by showing these different images of the same object, the neural network also becomes more robust towards these changes. And so now, if it's trained with both of these images, it is far more likely that it is robust to illumination changes. And finally, we can not only do cropping as we showed earlier, which is from one image we obtain 5 crops, which are essentially top left, top right, bottom left, and bottom right corner, and the center. But we can actually do random crops to generate even more variations of an image. So here is one way of doing random crops, where you actually pick a random variable, you assign one value, and you resize the training image such that the short side actually is actually of the length L of this value that you have chosen before. And then you randomly sample crops of 224 by 224. Again, this is the input that AlexNet needed, so this will depend, of course, on your neural network. And during testing, what you can do is then take a fixed set of crops. So not doing the random cropping both at training and at testing, but only during training. And then at testing, you actually resize the image at different scales, and you take 10 fixed crops, for example, which is again the idea of taking the 4 corners plus the center multiplied by the 2 flips. And you actually test all these variations and see if you obtain a coherent output. So data augmentation is actually one of the simplest ways to improve the classifier accuracy. But when you're actually comparing two networks, let's say you're trying to improve your architecture, you have to make sure to use the same data augmentation, because sometimes data augmentation is randomly computed during training. And this means that your two networks are not going to receive the same data augmented images. So therefore, they're going to be trained essentially with two different sets of images. So if you actually want to compare two networks and know which one is best, make sure to use the same data augmentation for both. And you also have to consider the data augmentation. So what type of data augmentation you do, you actually have to consider it as part of your network design. So this is one hyperparameter that you actually have to play around with, that you actually have to try to see if it actually works for your problem. You can actually see data augmentation as a form of regularization. So you actually want your neural network to generalize better, but most likely your training error is going to go up as you increase your data set. You increase the variety that you can find in your data set with all your augmentations. So you can actually consider it as a regularization method. And there are other types of more advanced regularization that we can use to actually increase the performance of our neural networks at test time. So one of the simplest ways of doing regularization is by using weight decay, which is essentially L2 regularization. So let's look here. We have an iterate step of the weights of our neural network. We have our learning rate, we have our gradient, and essentially we're going to add this orange term here. This orange term, which is weighted by lambda, and it's essentially the gradient of the L2 regularization on the weights. So again, as we saw in previous lectures, the regularization acts only on the weights, which is why this term has dependency only on these weights theta k. And this term, essentially what it does is it penalizes large weights. So if you have these two cases in which you have all the weights concentrated in one neuron, and the other neuron is essentially doing nothing, so the weight of this neuron is actually 0, what is really happening here is that you're putting all the classification power in just one neuron. So what weight decay does is it says, I'm going to split the weights between two neurons. So it's much better to have theta half here split between the two neurons than to have only one neuron taking all the power. So you can imagine also how this plays at a higher level, where we're, for example, building a classifier of a face, and we have two neurons, one that classifies eyes and one that classifies the mouth. So would you rather trust the classifier that places half the weight in classifying the eyes, places the other half of the weight in classifying the mouth, and then tries to reach a consensus between eye classifier and mouth classifier to actually say whether this is a face or not? Or a classifier that just focuses on the mouth entirely, and as soon as it detects a mouth, then it says that this is a face. So of course, when we're playing at a larger scale of a neural network with millions of neurons, you can imagine how this effect actually amplifies, and actually allowing the decision to be divided between several neurons is much better than allowing one neuron to become very specialized. So in the case of the left, here where we place all the power to one neuron, it is much more likely that we actually overfit to the training data. So this is why with this simple technique with weight decay, we penalize large weights, and therefore we allow this second configuration to come out actually in a much more likely way. And this, as I've said, really improves generalization, so really improves the performance at test time while probably decreasing the performance at training time, because of course we're adding this regularization here. So another type of regularization is early stopping. Again, very, very simple regularization. So as you will be training neural networks, you will see that you're constantly looking at this kind of graphs. So the loss as it evolves in time, as it evolves in your epochs. And ideally what you would like to see is you would like to see the training loss go down, but also the validation loss going down. So you always have to monitor both. And as soon as the validation loss starts to go up, it means that we start overfitting. And therefore, what we can simply do is we can monitor the validation set loss. And as soon as the loss starts going up and we start overfitting, we essentially stop the training. So we pick the point where the validation loss was lowest and we stop the training there. We get that model, and this is the model that we use at test time. So this is a very, very simple way of applying regularization, kind of manual regularization, but this is actually really effective. And you can actually view this as essentially an evolution of your weights, right? So your weights are evolving with this, with the learning rate, so faster or slower depending on the learning rate. And this weights evolves until we reach this point, theta s, in which any further evolution will mean starting to overfit. And essentially, we want to find that special point theta s, that optimal point in which we had the lowest training error and the lowest validation error. Now, another type of simple regularization is to use bagging or to use ensemble methods. So essentially what we do here is we train multiple models. So for example, you have your data set, and instead of training one neural network and applying weight decay and early stopping, you train 3 neural networks. So you have several models that have looked at the data in a different way. And by a different way, I mean that, for example, you can use a different algorithm to optimize your neural network. You can change the objective function or loss function. You can use different mini batches. You can shuffle the data differently. You can use different data augmentations, anything that would lead to different optima in the different models. And then the idea is that if the error that your neural network is making, if all of these errors are actually uncorrelated, then the expected combined error will decrease linearly with the ensemble size. So essentially, the more models I have, the more my error will actually decrease. And this is, of course, assuming that the errors are uncorrelated, and this is the key point here. Bagging is a very similar concept, so still the idea is to build different models that lead to different outputs that you can actually compare so that you can create a more robust output. And how these models are actually differentiated in bagging is by using k different datasets. So you take your dataset, you take your training set, and you divide it into k parts. So these parts can be overlapping, but each of these small training sets, training set 1, 2, and 3 in this case, are drawn from the bigger training dataset and are actually a subset of this dataset. So you can imagine how in training set 1, we will have, for example, a lot of black dogs, and in training set 2, we'll have a lot of white dogs. So the first model will become specialized in black dogs, and the second model will become specialized in white dogs. And the idea is that the combination of these models is actually what makes the prediction so strong, because each of them is specialized in subtle different things, and therefore the combination is actually more powerful. But of course, here what we're doing is we're actually training 3 different neural networks. So this is really expensive. So the question is there a way to do a similar thing without really training 3 separate models? And this is where the technique Dropout comes in. Dropout was proposed in 2014 as a technique for regularization. So the idea was that you would train a standard neural network, and at some point you would disable a random set of neurons. So let's assume that our dropout probability is 0.5. In this case, what we do is during the forward pass, we disable 50% of the neurons. So you can see here the standard neural network on the left and the neural network after applying dropout on the right. So all the nodes that have the crosses are the nodes that are not going to be used in the forward pass. So you can see that essentially what we're doing is we're taking our standard neural network and we're reducing its capacity substantially. We are actually taking out 50% of the neurons, which also means that if we're using half of the capacity, we also have half of the expressiveness. So in the intuition behind why dropout is a regularization technique is because if we are building a classifier, let's say a dog classifier, and we have certain characteristics that our neural network has learned. So there are certain nodes that are responsible for detecting whether there is the furry characteristic in the image, whether there are two eyes in the image. Other neurons detect whether there's a tail in the image, etc., etc. So several neurons have been specialized to detect all of these characteristics, and now suddenly you drop half of them, so you ignore half of them. Effectively, what you are doing is, instead of using all the small classifiers, all the characteristics to make a decision, you use only half of them. So now suddenly what has happened is that your neural network is no longer able to detect whether there is a tail in the image or whether there are two ears in the image. So the neural network has to make the decision with much less information. So this is what happens during the forward pass. But what happens during the backward pass? So of course the neural network says, hey, I don't have any classifier, any neuron that is responsible for detecting ears. So effectively what I'm going to do is I'm going to use my gradients to actually reprogram some of the neurons that are actually active to detect ears or to detect tails. So what this creates at the end of the training process is a set of redundant representations. So instead of having a set of neurons that is responsible for detecting eyes and all the other neurons ignore the area of the eyes of the dog because they know that there are two neurons that are responsible for detecting eyes, what happens during dropout is that these two neurons are dropped out randomly, but it is possible that these two neurons are dropped out. So the network is left with no capacity to detect eyes. Therefore, other neurons have to learn how to detect eyes. So now instead of having very specialized neurons to detect eyes, you have another set of neurons that is also responsible for detecting eyes. And the two sets of neurons responsible for detecting eyes are going to be trained with slightly different images, of course, different mini batches, etc., which means that they will learn two different representations of eyes. Hence, the neural network is going to be more robust because it's going to have more than one way to detect eyes in the image. So the fact that we're using half of the network actually creates redundant representations during training. And so essentially what you're doing is you're basing your scores on more features. So as I said, instead of relying on a series of neurons that are specialized to detect one particular set of eyes, now I have several neurons, they're all detecting eyes, and I'm going to base my score on all of these neurons instead of two very specialized and often overfitted neurons. And so you can consider it actually as a model ensemble. And I'm going to be more precise here. So if we have a dropout probability of 0.5, what you can consider is that you're using half of the neurons, the half that is active during a forward pass, to construct model 1. And so these neurons, these orange neurons, are going to receive a set of images, the images that are present in the mini batch, and are going to be trained with those set of images. Now, the other model is the model of the neurons that were not active during that forward pass, so the neurons with the crosses. And these neurons are going to be trained at another epoch with another set of images. So, of course, the dropout probability doesn't work exactly like this because it's not that I deactivate all the orange neurons in one iteration and then I activate all the orange neurons in the next iteration. So for every iteration, there is a probability of 0.5 of a neuron being dropped. But statistically, this is what ends up happening. So you can imagine it as having two models, the models of the active neuron and the models of the inactive neurons, being trained within one training cycle of a neural network. So instead of actually training a large ensemble of models with completely different networks, what we do is we train a large ensemble of models, all with the same network, therefore we share parameters, but each of these models is now trained on a different set of data, therefore on a different mini batch. And there's a large ensemble of models because every time I draw the probabilities, and every time I decide whether a neuron is active or not, I am creating a different model because I'm creating different connections depending on which neurons are active and which neurons are not active. And eventually what this leads to is a reduction in co-adaptation between the neurons. That is similar to the concept that I've explained before, that a neural network has two neurons that are very good at detecting eyes, and therefore all the other neurons ignore the eye area completely because they know that they can rely on those two neurons to detect the eyes. Now, if those two neurons drop out, the neural network has to somehow arrange itself to learn to detect eyes again. So essentially what you do with dropout is you reduce co-adaptation. So you reduce this act of neurons depending on other neurons to do their job because their other neurons have already been trained, for example, to detect eyes or to detect ears. And this is very, very important for good generalization of your neural network. Now, what happens at test time, right? So for now, we have talked about the process during training. So during training, you decide for each neuron whether to drop it or not. You create your model, forward pass, backward pass. But what happens at test time? So at test time, you're not really interested in applying dropout. You're not really interested in doing your prediction with half of the neurons. You're interested in using all the neurons, and hence all the neurons are turned on. So there is no dropout during test. So you can see already that the conditions at training and test time are not exactly the same. And we're going to have to adapt a neural network to match the conditions at test time. So let's look at this particular example. We have here two variables, x1, x2, multiplied by their weights, θ1, θ2, and this actually creates the output variable z. When we have dropout, this output variable z is multiplied by a probability p, and this is actually the dropout probability, which typically we set to 0.5. So another question is, what is the expected value for z? So we know that during training we can have four conditions. The first condition we see here is that both of the neurons are basically dropped, and so we have basically a 0 in there in both inputs. The second condition is when x1 is active, third condition x2 is active, fourth condition both x1 and x2 are active. And if you actually compute the expected value of z, what you end up having is this 1/2 in front of your operation θ1 multiplied by x1 plus θ2 multiplied by x2. And this corresponds exactly to the dropout probability. So what you have to do is what is called weight scaling inference rule, which is at test time, you have to adapt your weights to match the conditions at training time. And this adaptation usually happens by multiplying with the dropout probability. So essentially, dropout is an efficient bagging method with parameter sharing. You should really try it when you're training a neural network. You find an optimal set of hyperparameters, you're happy with your performance. Just try to apply dropout. Usually this brings a slight accuracy boost. But you have to take into account that Dropout reduces the effective capacity of a model. So it can be that you actually need a larger model to apply Dropout, to train it with Dropout, and hence you're going to need more training time. So this is something that you have to take into account when you want to apply Dropout. While Dropout was actually very popular some years ago, now for most networks, we actually use some form of normalization as the best regularization technique that we can actually do. And so we turn to explain batch normalization. So remember the example that we had, where we had this neural network with 10 layers, and we made this experiment where we input a unit Gaussian, and then we see how this unit Gaussian actually evolves. So how the neural network treats it if, for example, we initialize our network with very small weights. And we remember that we had this case at the top where all the values were collapsing to zero. And if all the values were collapsing to zero, we had that the gradients were dying during backpropagation, and therefore we cannot train our neural network. So one of the ways to solve that was to do a proper initialization. And we saw techniques with Xavier Initialization or Xavier half initialization in the case that we're using ReLUs that were actually able to maintain our activations. And so now the question is, well, if our goal is that our activations do not die out, why don't we actually do this? So my wish is that if I input a unit Gaussian, then after the processing of the layers, I still have unit Gaussian activations. So I don't have activations that are collapsing to zero or activations that are essentially exploding and overloading, saturating my nonlinearities. So if this is my wish, why don't we actually do it? Why don't we actually implement it after each layer and put this constraint that I actually want to have a unit Gaussian in the output? So what I'm going to plot here is the number of training samples, so the minibyte size n, and the number of features d. So here what I have in each of the column is for all the training samples, feature 1, another column feature 2, feature 3, until feature d. And so what I'm going to do is I'm going to essentially apply a forced normalization on these features. So I'm going to take the mean of the mini batch over feature k, hence these columns here. This is the mean of feature k. And I'm going to normalize this vector. So what I'm going to enforce is that in each of the dimensions of the features, you actually have a unit Gaussian. I had a unit Gaussian at the input, and I want to have a unit Gaussian as output. And so now for each of these columns, what I'm going to do is I'm going to normalize it and convert it into a unit Gaussian. Again, this conversion is just subtracting the mean, dividing by standard deviation. This is not converting any distribution into a unit Gaussian. This is just because I had a unit Gaussian as input and I want to have a unit Gaussian as output. This is only in our example. In your example, you're going to have a distribution as input and you're going to normalize it in the output. So the key here is this normalization that doesn't allow collapsing or saturation in the output. And so for neural networks in general, the batch normalization normalizes the mean and the variance of the input to your activation functions. Now, typically, this is represented as a layer. So there is a batch normalization layer. And this layer has to be applied after the fully connected or after the convolutional layers and before the nonlinear activation functions. So, of course, we don't want to pass all the information through the nonlinear activation functions because this could easily saturate. So we want to nicely normalize the feature map before passing it through the nonlinear activation. And so batch normalization usually contains two steps. The first step is the one that we have talked about, is the normalization step. So if you look at this operation, this is a differentiable function, so we can actually backpropagate through it. So no problems here, this is a fixed operation. But batch normalization is not only about this operation. There is actually a second step. And this second step actually allows the network to slightly change its mind. So what I mean by this is that we have forced a normalization onto the network. And maybe this normalization is not the best for the network to learn certain characteristics of the training dataset. Therefore, we're going to allow the network to slightly change the range in which this normalization is done. So in the extreme, the network could undo completely the normalization. And how this is going to happen is with this second step, in which we're going to take the normalized output here. So this is the output that we have just normalized. And we're going to multiply it by these two parameters. We're going to, multiply it by gamma, and then we're going to sum beta. And again, these parameters are different for each of the feature dimensions. And these parameters are not fixed parameters like they were before, right? This normalization is with fixed values. But beta and gamma are two parameters that are going to be optimized during backpropagation. So these parameters are going to be learned together with all the other parameters of the neural network. And we're going to learn them through backpropagation, the same as any parameter in a neural network. So let us now imagine that the neural network didn't like our normalization, thinks that our normalization is horrible for its purposes to learn certain characteristics. And let's imagine that after training, these two parameters, beta and gamma, actually converge to these two values. So beta converges to this value here that we subtracted earlier, and gamma converges to the value that we divided our input by earlier. So essentially, if you look at this operation, what it's doing is it's taking this value here and multiplying it by the square root of the variance. Before we divided, now we're multiplying, hence the two terms cancel. And now what we're doing is we're summing beta, which is this value here. And of course, if I sum beta here, what essentially I have is, again, a cancellation of these two values. So what I did in this process is I normalized first, then I trained these two parameters, beta and gamma, and the network decided to completely undo the normalization. And so in the end, what I obtained is the same input xk that I had at the beginning. So this is what essentially makes this technique so flexible. I impose a normalization. This normalization guarantees that I have good and stable gradients, that nothing saturates or nothing collapses to zero. But still, if this normalization is going to hurt the performance of the network can still learn to completely undo the normalization. Of course, this is not something that typically happens. Here we just want to show that it is possible to undo the normalization. So we're not taking out any freedom from the neural network. So now one question that you might ask is it actually okay to treat these feature dimensions separately? So each of these parameters that we saw here has this index k, which means that it is absolutely different for each feature dimension. So for this, we just have an empirical result that even if the features are not correlated, the convergence is still faster with this method. So again, this is just an empirical result that actually shows that batch normalization in this particular way works really well, and the convergence of neural networks that have batch normalization is actually very fast. And this is just a small thing, but it is important to see why you should actually set all biases of the layers before the batch normalization to 0. And this is because all these biases will be cancelled out by batch normalization anyway. So these are parameters that you would be essentially wasting. So you can directly delete them before applying batch normalization. So what happens with batch normalization at test time? So at train time, it's very clear. We can compute the mean and variance over the mini batch. But at test time, usually what we have is just one image, right? We want to classify one image, and therefore we process one image at a time. We don't have often the concept of a mini batch at test time. So there's really no chance to compute a meaningful mean and variance with just one image. So how should I actually apply batch normalization at test time? Well, during training, again, what you do is you compute the mean and the variance from all the mini batches, and you store these values. Now, what's going to happen at test time is that you're going to run an exponentially weighted average across the training mini batches, and you're going to use these values for test time. So essentially, you're going to use the values, the mean and the variance that you computed at training time. You're going to compute this exponentially weighted average, and you're going to use this value during test. So essentially, during test, the test value for the mean and variance are fixed as obtained during training. So essentially, what do you get from using batch normalization? Well, the most important thing that you get from batch normalization is that your now very deep networks are going to be much easier to train. You're going to have much more stable gradients, same as we saw with the simple example of the initialization and how a good initialization completely changed the training behavior of neural networks. This is just going to be amplified here with batch normalization. So now what you can do is you can create much deeper networks and you can actually train them easily. And also, there is a much larger range of hyperparameters, learning rate, etc., that actually works in a similar way when you use batch normalization. So you can actually reach decent results without having to do crazy hyperparameter tuning. And so one can consider batch normalization to be a true milestone. So you can see all the methods before 2015, AlexNet, Overfit, Inception, that were not using batch normalization, and how the top one error in percent was always above this 26-27%. As soon as batch normalization appeared, one can create deeper networks, one can better train those networks, and results are improved a lot with networks that are using batch normalization, which are here depicted in blue. So you can see that after 2015, all the networks that use batch normalization actually have an error that is usually lower than 25%. But of course, batch normalization has drawbacks. So as we reduce the batch size, the statistics for our mean and variance get less and less accurate, and batch normalization starts to deliver not so good results. So we can see here that for a batch size of 32, 16, the validation error stays quite constant, but as soon as we reach batch sizes of 8, 4, and especially 2, the error grows quite a lot. So essentially, one cannot use batch normalization with really small batches. But there are other normalizations possible, and in particular, group normalization is another type of normalization that stays quite constant, so the error stays quite constant even if the batch size is reduced quite a lot, even to the extreme of getting to a batch size of 2. And so how do these other normalizations actually look like? So here's a nice depiction that appears in the group normalization paper. So here we have our feature map during batch normalization. So our feature map contains the spatial sizes H and W, contains the number of channels, and contains the number of training samples. And batch normalization, what it does is for one feature dimension and for all the training samples, it normalizes the values that are depicted here in blue. Now, the agent W, again, is the image size. So in this case, the spatial size plays no role in any of these normalizations. So this is for batch normalization. There is also layer normalization, that instead of normalizing across the training samples, it normalizes across the channels. There is instance normalization that normalizes simply across the spatial dimension. And finally, there is group normalization, which is like a hybrid. So it does normalize some feature dimensions, but it doesn't go across the training samples in the mini batch. So it doesn't normalize across training samples. And this is why you can actually make it work for large batches, but also for small batches. It's time for a recap now to ask ourselves, what have we learned so far? So we started by introducing the concept of neuron, the concept of neural network, multi-layer perceptron, and this idea that we keep processing the information as we go deeper into the network, that we have a series of neurons that define the width of our network, and that this whole processing of information together with the linear operations, the nonlinear operations, is actually very powerful for tasks such as image classification. We introduced the concept of a neuron. So what exactly are the operations that are inside this neuron? So it's not really black magic. It's a set of linear operations plus a nonlinearity that brings this score to a value that is, for example, between 0 and 1 in the case of a sigmoid. And the cascade of these operations is actually what makes neural networks so powerful. We also saw different activation functions, different nonlinearities, how sigmoid is no longer used, even though people started using sigmoid and TanH, but quickly moved to ReLU and leaky ReLU, especially in the case of convolutional neural networks, which is something we haven't seen so far. And we saw actually how to train these neural networks, how to backpropagate the gradient, how to train these 100-layer neural networks through the simple chain rule, simple backpropagation. We also saw different optimization algorithms, which are mostly SGD variations, how each of them presents different characteristics, and what kind of optimization methods do we typically use nowadays to optimize our large neural networks. And finally, we have seen, especially today, regularization techniques, data augmentation, batch normalization, dropout, proper initialization, what is the effect of initialization in training neural networks. So all very important aspects that actually make neural networks trainable. And so we can actually digest all this amount of data that we have, that we need to process in order to obtain this high performance for a given task. So now the question is, how can we proceed further, right? We have our multi-layer perceptron, we know how to training, we know the elements inside our neural network perceptron. So what kind of other steps can we take to improve performance, for example, on image classification? So why just not create deeper and better networks? We have batch normalization, we can create really huge networks. So is that really the way to go? Well, it turns out that if you create just deep multi-layer perceptrons, you're missing a bit of a structure. So it's like doing a brute force approach. And optimization is going to become harder and harder as your network becomes deeper, and also your performance is going to plateau, or it's even going to drop. Your network is essentially going to overfit and it's not going to generalize. So in order to take one step further, what we're going to do in the next lectures is we're going to introduce a little bit of structure into our neural networks. And this structure is very much suited to process images. And therefore, you can already imagine that I'm talking about convolutional neural networks, and this is where we are headed for the next 2 lectures. So thank you very much for your attention, and see you next week with convolutional neural networks.